Good afternoon, everyone. Nice to see more people here today. Our population's growing. We're up to, I think, 12, which is, what's that in percentage? Like 3%, 2%, 3% of the class? So, welcome. Nice to see some actual faces here, too. Uh, I love all you people online as well. I mean, don't get me wrong. Online or in person, both are fine. Or watch the video later. That's okay, too. Um, a couple of maybe housekeeping things. I sent an email out this morning, and I think a reminder earlier in the week about those weekly quizzes. Not weekly, they're unit quizzes. So every unit, whenever we finish a unit, 7 days later, that little quiz is due. I've been watching them, and most people seem to be just doing them as we do them in class, which, if that's the case, then it's really no work outside of attending class. Just make sure that you keep an eye on those. There will be several of them throughout the course, probably about 10 or 12. So just make sure that you are keeping up with those and making sure that you don't accidentally miss one. What I'm trying to do is as soon as we finish a unit on Acorn, I'll go ahead and post at for the assignment what the due date is in all caps. And then what I'll do is when that deadline passes, I'll change the due date to completed. So that just helps you keep track. So what I'm expecting is at any point you can go onto the Acorn webpage for the class and see the due dates for everything that has a due date set so far. And if it doesn't have a due date yet, it just is blank, or it might say TBA or something like that. For example, just a few minutes ago, I opened up the unit quiz for this next quiz that we're going to be starting today, which is on elements of chemistry. And so I didn't put a due date on that yet because I don't know when it is exactly that we'll complete it. It'll be 7 days from that point on. I sent an email out sometime in the last week about assignment 1, and I'm happy to see people are already submitting those, so that's great. I don't think it's like a crazy amount of work to complete this assignment. If you've already done it, fantastic. If you have any questions, you can let me know, although I tried to be as clear as possible. The main takeaways: make sure it all fits onto one page. I don't know if I made that clear enough in the description. No cover pages or anything like that. No bonus pages at the end. And just follow the guidelines. I think, I've had similar assignments over the years, and I think I put all the FAQ in the description for that assignment. In fact, I think the description for the assignment might be longer than your assignment needs to be. So just make sure that you are aware of that. All right, can people hear me online okay? Sounds a little muffled, what they're saying. Okay, let me crank that up. Is that better? All right, I don't know why. Might be just the positioning of this changes it just a little bit. Yeah, online people, if you can let me know if that's a little bit better. I adjusted some things. There we go. Perfect. Great. What else? Well, we're starting a new unit today. Let's go to our new unit. Our unit's going to be on the elements of chemistry. So we spent quite a bit of time talking about, a little bit of how chemistry and science in general is portrayed in the media. We looked at pseudoscience. We looked at a number of different examples of, how science can be used and abused. And we had that one unit in the middle on toxicology, which really did address some concerns, or some public perception, at least, concerns about chemicals, and maybe a more scientific way to think about them. What we're going to do in this unit is rewind the clock thousands of years and kind of take a look at how the science of chemistry developed, where it came from, and hopefully along the way peg a couple of very important discoveries which are central to our modern understanding of the science of chemistry. And these are things we can apply to everything in our everyday lives. These aren't weird, obscure kinds of discoveries, or these are sort of big fundamental things that we ought to understand in order to really understand the world that we're living in. Great. So we're going to go back 400,000 years. And we're going to look at the first chemical reaction that was actually controlled by human beings. Because if you look at say chemistry as maybe the science of humans being able to control chemical reactions, put those chemical reactions to use, and maybe even understanding what's taking place in those chemical reactions. Probably one of the first ones was our ability to control and use fire. And there's arguments among archaeologists when human beings as a species managed to control fire, ranging from 1.7 million and sort of the most recent estimate. In other words, the most conservative estimate is 400,000 years. We're certain at that point in time human beings were able to make and control fire. And if you imagine humanity before fire and what fire brought to us in terms of our ability to survive, it was tremendous. I mean, it brought us warmth, so it allowed human beings as a species to expand into colder climates. It provided protection against maybe certain animals or predators. It allowed us to cook our food, which increased the amount of nutrients we could get from our food. It also made the food safer because it could kill pathogens that might be present in our food. So it had health benefits as well. And if you think about it, fire also needs to be respected. It's potentially dangerous. You could imagine if you had a crude home made out of wood, it could burn down and pose a risk for people inside. So I think this is a neat example, I think a very early example of one thing that I'm trying to get across in this course again and again is that our ability to understand and control a chemical reaction should bring us benefits. On the whole, I think overall bring us benefits. But that does not mean that those advances are not also without risks. So again, whatever chemical process we want to make use of, we need to understand and be able to put in context the risk versus the benefits for all of these things. Fire being the first example. Along the bottom of the slide here, I have a chemical equation. And this is sort of the language of chemists. And it's one aspect, I guess, maybe of the language of chemists. Kind of just like, musicians, the language of music is the staff with the notes and the rests and all that kind of stuff. It's like a notation that's used to convey a particular idea. So what this is showing is chemical reaction where we have an arrow separating the left side and the right side. Everything on the left are starting materials. Those are chemical substances that are present at the beginning of a chemical reaction. And on the other side, you have products, which is what those starting materials get converted into through a chemical reaction. You can see that C6H10O5. That means that's a molecule with 6 carbons, 10 hydrogens, and 5 oxygens. And that's sort of a representation, crude representation of wood. Wood is a very complicated substance made of many different kinds of molecules, but that's sort of like a rough ratio of the elements. It's reacting with 6 equivalents of O2, which is oxygen gas, to make carbon dioxide, water, and heat, which is, one of the main reasons we use fire. After the domestication of fire, 400,000 years ago, we moved into the Bronze Age. I mean, there's a bit of a gap there. Maybe there's a couple of things we discovered in between. Bronze Age ran from roughly 3300 BC to about 1200 BC. And this was an age in our history which is dominated by our ability to create bronze metal and then create objects out of that, including weapons, including, pottery, coins. And this discovery allowed us to develop many aspects of our modern civilization. Like trading became a lot easier. I guess fighting became a lot easier. But, again, pros and cons. Chemical reaction for the production of bronze is shown below. It's carbon is the C plus 2 different minerals that you can find, copper oxide and tin oxide, and it makes carbon dioxide, and then a mixture of copper and tin metals, which is bronze, which you can see in this particular $3 coin, which was made in 2013. It's actually believed that the development of bronze actually was one of the first most heavily traded commodities or goods, because copper oxide and tin oxide are typically not found together in geological formations. So what would often have to happen is one area might have the copper oxide, another area might have the tin oxide. They'd have to trade with each other, not just trading locally, but over large distances, which of course enabled the production of bronze. Iron Age came after the Bronze Age. It was another chemical reaction. It's actually interesting how we section our history in terms of our civilization, in terms of our understanding of chemistry. Right? The Bronze Age, we understood chemically how to use that process. Probably the people making bronze and making iron had no concept of what was physically happening to these substances they were mixing together. But what they did know is that it produced a substance that was useful to them. So iron had a lot of advantages over bronze. It was a lot tougher, a lot stronger. That's made by taking copper, which is charcoal, which would be present in, if you have a fire and you put the fire out, you have charcoal that's left over in there. That will react with another mineral that you can find called iron oxide, Fe2O3. That means there's 2 iron atoms for every 3 oxygen atoms in that substance. That reacts to make carbon dioxide and iron. And you can almost picture how somebody might have discovered this by accident. They had a campfire going, they put it out. There happened to be minerals in around the campfire that contained iron oxide. They started a new fire. Chemical reaction took place between the charcoal that they had in there and the mineral that was there. And somebody noticed that there was this sort of like silvery substance being produced. And then they found, well, if you heat that up, maybe you can melt it and make it whatever shape you want. And then, of course, that's how this idea kind of took off. Lots of other early discoveries important in chemistry that had obvious advantages for civilization. Soap making was a big one. Hard to imagine living in a world where we didn't have soap, not just for maybe our own hygiene and smell and so on, but in terms of like disinfectant, making sure like you could clean your pots and dishes and things like that, and all the other reasons why it's important for us to have soap, which is maybe doubly important now that we're grappling with COVID. Right? So, you're being constantly told to wash your hands. That chemical reaction is starting with fat. You can find in any animal or often plants too. Reacting with lye to make soap and glycerin. And it turns out if you burn wood and you get a bunch of ash at the end, like white ash, if you burn it all the way down, that white ash contains calcium carbonate is in there, which is most of it, but there's also strong base, NaOH, or calcium hydroxide as well. Those ashes can be mixed with fat and do this chemical reaction. You can make a crude soap that way. So probably, again, that was an accidental discovery where people had fat heated in the ashes of a fire, and then all of a sudden they saw like a soapy substance when it got wet. They found it could be used to clean things, and so on and so on. Leather tanning, some people believe that is as old as 7,000 BC. And what this does is it's a process for treating leather in order to make the leather softer, more durable, and more resistant to breakdown. And this is a tannery, an old picture of a tannery. And the way they used to do it was actually really gross. They just knew you had to put a bunch of weird substances on leather and rub it in for like days. And they used to use feces. So like they'd rub that in and it would like stain it different color and it would smell awful, but like it would keep the leather, that we wouldn't use just that. They'd use like plant extracts, teas, all kinds of things to try to make the leather last longer. That got perfected over the years when they found which substances worked better than others. And I don't even know what they use now. They probably use synthetic chemicals. Fermentation is a big one, right? Fermentation is a process taking sugar and turning it into alcohol with the help of yeast. And so this was used to make beer and wine. They have evidence that it's at least from 5400 BC from archaeological evidence found in Iran. Probably older than that. Definitely biblical times. Talks about wine all the time. So yeah, definitely a very old chemical process that we figured out how to use. So around the year 0, okay, there was a sort of a rise in certain areas, certainly Greece, Rome to a certain extent, of philosophy. And there's a lot of philosophers, and the classic philosophers that you think of, like Plato and Aristotle and people like that, spent a lot of time pondering the nature of, I don't know, everything like ethics and so on. But they also spent a lot of time pondering the nature of our material world, because basically nothing was really understood at that time. Like, a lot of people just believed everything that exists happens for just unknown, potentially supernatural reasons. And it probably never occurred to most people to try to investigate our natural world to learn what makes things happen. The philosophers did actually spend a lot of time talking about this and thinking about this. And at the time they developed the belief, or they posed the theory at least, that every substance that we interact with, every chemical, can be broken down into what they called elements, which are fundamental materials that can be combined to make every substance that we know about. And they believed there was 4 such elements. And these elements are written here: water, air, fire, and earth. So the idea is, you take a piece of wood, for example, which is chemically very complex. Take a piece of wood, it's a combination somehow of these 4 substances, or 4 elements, was the thinking. So you take a piece of wood and you could burn it. They knew if you burn wood, it would give off water vapor, so you could see the water come off. They knew it made smoke and some kind of gas. That gas we now know is carbon dioxide, which they would have called just air. Fire, obviously. Fire is coming out of the wood, it looks like, at least, when that wood is burning. And then finally, when it's done, you have ashes, and they said, well, the ashes would be the earth part. So by burning the wood, you're separating it into those elements. You can see all of those elements. And this was sort of their working hypothesis in terms of what all of matter is composed of. In fact, some philosophers added a 5th one, and the 5th one was called the ether, or sometimes the void. And what that was basically empty space. So you could also have nothingness as one of those elements. But I think the well accepted ones are certainly the 5 classic ones. So this is what the periodic table might have looked like at the time, if somebody had thought to put it together. Just those 4 elements called the classic elements, none of which we now know are actually really elements. All of these are things that are composed of either multiple different substances or can be broken down into more simple things. So even though we know that these classic elements aren't actually like a real thing anymore, the idea of the 4 classic elements certainly has persisted. And this is a harmless advertisement. This is just like an advertisement for a spa, I think in a hotel somewhere, where there's a 4-part spa treatment you can get, and it's themed after these 4 classic elements. There's the earth, I don't know what it is, a mud facial or something like that. Air, I don't know what's going on here, but you get the idea, right? Like, so this sort of idea of these fundamental particles still kind of exist. And really, in a way, they kind of had something correct about these 4 substances. While we know now that they're not really the 4 elements that everything's made out of, what we do though is we describe every substance that we come into contact with as being some state of matter. And those states are solid, liquid, gas, and plasma. And each of those correspond to one of the 4 classic elements, where a gas, air, is a gas, water is a liquid, earth is a solid, and fire is a plasma. And plasma might be one you're not familiar with. All a plasma is really is a gas where all the particles in the gas are charged. So normal gases, everything is not charged, it's neutral. So arguably plasma is a type of gas, but for our purposes here, we're going to make them line up this way. Question 1. So this is now open. If it's not, please let me know. Great. Glad the people online can hear well. Yeah, which of the following substances is not one of the four classic elements? And we have fire, water, earth, salt, and air. So yeah, that shouldn't be too challenging. Atomism. So Democritus, 500 BC. He was one of the early philosophers. He believed that all material was made out of two different things, which he called atoms and void. Atoms were bits of matter which were not divisible. In fact, the word atom means cannot be split, because the word the tom, it must be a Greek root, means to cut. And you still see that root in some English words, like a lot of medical terms. So if you get your appendix removed, it's an appendectomy. The tommy at the end means to cut. So you're cutting out your appendix. Or a tonsillectomy. So yeah, that tom means to cut. And so if you put an A in front, it means not. So you cannot cut something. It's an atom. So he just said, matter has, at some point, you can't cut it anymore. You get these indivisible units, which is really our modern understanding of how substances are built. We have these little atoms, which are very, very small. And then he said, other than those atoms, there is empty space, which we call a void, which we also believe to be true. He went on to say that atoms are indivisible, indestructible, uncreatable, and eternal. And that is really more or less our modern understanding. And you know, there's some fringe cases. We know that you can actually make some atoms in particle accelerators and supernova and stuff like that. And we know that you can split atoms too, like those are nuclear explosions and a nuclear power plant, you're splitting atoms. But by and large, every day, like your everyday chemical reactions, you're cooking your food, you're burning stuff in your fireplace, all those sort of routine, mundane reactions, the atoms are not being destroyed. They're always kept intact. Whatever atoms are present initially, they're always still present at the end. They don't disappear, and they don't come out of nowhere either. Okay, and we're going to look at that idea just a little bit more in a little bit. The last statement there is that he believed matter is quantized. So this is just a fancy word, meaning it appears in discrete amounts. And that discrete amount is an atom. It's the sort of fundamental unit of substances. So this was like a really old idea, which is actually quite an interesting thing that he came up with this idea, because he really didn't have any kind of evidence to support this. They had no really scientific way of testing this. So this, if you remember when we talked about scientific theories and scientific laws, this isn't really either of those, because it was kind of untestable. It was more of a hypothesis than anything else. And it actually didn't last that long. Plato kind of shot him down. Plato said, no, that's not true. He went back to the four classic elements, and he actually believed, like Plato actually had a real love for mathematical figures and mathematical shapes, and he believed there was something fundamentally special about what are now called Platonic solids, named after Plato. These are solids, just geometric shapes, three-dimensional, where all of the faces of that shape is a regular polygon. So if you took 6 regular like squares, which are regular polygons, and put them together, you make a cube. He thought that was a fundamentally important shape. If you took triangles, took equilateral triangles, you could make the top shape here, which is called a tetrahedron. And you can make those other shapes that you see down below as well. And he believed that the 4 most basic Platonic solids, the 4 simplest ones, corresponded somehow to the 4 elements. And he thought there was this relationship somehow between how matter was built and these shapes. So fire, he knew, it would hurt if it touched you, and it was very vigorous. It would cause reactions to happen. It would cause things to burn or decompose or break down. And so he thought this one was the tetrahedron, because that one is like got sharp corners, which made him think fire. Notice the cube. A cube is, out of all of these, like the most solid. Like it'll sit down, it packs, you can make it dense, doesn't roll very easy. So he thought that was like Earth. The icosahedron was the most ball-like, which could roll maybe. He thought that was like water, because water is a liquid and it can flow. And then air, I don't know, maybe it was process of elimination. Well, air needed something, so we got the last one. But anyway, Democritus's atomic theory, which I guess now 2,500 years ago, was to be put away for many, many years. Aristotle came next. He believed that the four elements were continuous, meaning no atoms. You can continuously subdivide something infinitely until you had, basically nothing left. And he also thought that space cannot be empty. So that idea of a void didn't agree with him either. That there's something filling all space, which is also wrong. Like, to their credit, I mean, they didn't have really any scientific data to go on. These were all sort of philosophical arguments that were being made at the time based on a very limited amount of knowledge and understanding of our natural world. So, I guess it was a good first attempt, even if it did not really bear too much fruit. It is interesting, though, to know that people have been pondering about the nature of matter, what we're surrounded by, trying to understand what it is that we're interacting with all this time, going back thousands of years. So it's not, super, super new. Even though I'd say most of our chemical understanding has come in the last 100, maybe 150 years. Before that, we really didn't know too much. So from the Greek philosophers, maybe a few thousand years went by. We then found, sort of in the Middle Ages, the rise of alchemy, maybe starting around the year 1000. Records, of course, are poor for most of this time, so a lot of this we know more from the more recent past. Alchemists were sort of the precursors of chemists. Alchemy was kind of a pre-scientific, I'm not going to say pseudo-scientific, it's more pre-scientific investigation of substances and matter and interrelationships and reactions that might convert one to the other and this kind of stuff. The alchemists really had one main goal, maybe a couple of main goals, depending on how you look at it. And alchemy actually, it's still very much in our cultural lore, if you want to think of it that way. One thing they really wanted to do was discover how to convert base metals to gold. And base metals were just sort of commonplace metals that were known at the time. Lead was one of them. Lead was known to be pretty abundant, pretty cheap. The Romans used lead in their plumbing. So lead was, quite common, quite dense, and not that valuable. Gold, though, was extremely valuable right from the beginning. And all cultures that independently discovered gold all developed, the understanding that gold was valuable. And there's a couple of reasons for this. One is gold has a special property. Gold, it's one of the only elements, it's probably the most abundant element naturally, that does not react with oxygen. It does not oxidize, it does not tarnish, does not rust. That's not the case for almost every other metal. There's a few examples, like platinum is another one, but platinum wasn't really, platinum's pretty rare, it wasn't very well known. And because it doesn't rust or tarnish, that makes gold a fantastic substance for jewelry or anything ornamental or decorative. We know now it's great for electronics and a lot of other things as well, but at the time, if you wanted jewelry, you wanted gold because it would last a long time and it would not change its appearance. Where if you made it out of iron, 10 years down the road, you have rust. So that's not good. So the alchemists were very interested in gold, and not for the reason you might think. They weren't interested in gold because it was valuable and they wanted to get rich. That seems like maybe the obvious reason why you'd want to turn a cheap, abundant metal into gold. They thought the reason they were interested in it was actually more maybe altruistic or more philosophical. They believed that gold somehow had a special property that made it immortal. And there was something about gold that made it immortal. And they thought if they could figure out how to make other metals immortal like gold, maybe they could figure out how to make human beings immortal too. So they figured there was something called the elixir of life, which is some substance you can add to make a metal into gold and make that metal become immortal. And that if we drank the same substance, then we might become immortal too. And so this was really one of the main goals. And they believed in the existence of something called a philosopher's stone, that you might be able to chemically make some substance, some catalyst, we might understand it to be now, that would turn water into the elixir of life. That you could use this to turn lead and other metals like that into gold. And alchemy actually was quite interesting. There was a lot of ritual, there was a lot of spirituality, a lot of metaphysical kind of aspects to alchemy. And when I say lots of ritual, what I mean is, if you were to mix some substances together, you might have to stir it clockwise a certain way so many times. Then you might have to say a certain chant. You might have to say a certain prayer, like all these kinds of things. It was a very heavy ritualistic element to this process, and they believed that you had to get that process just right. And the way modern fiction talks about magic really borrows many, many elements from the way alchemy was practiced. So the idea of a magic wand would have been like a stir stick that they would have used to stir whatever they were stirring in a very ritualistic way. The idea of speaking magic words, to like a spell, that would have been something that they would have understood would be necessary to do a chemical reaction properly. You got to say the correct words. And you think of the sort of the old, in cartoons, you see witches and they have a big cauldron. They're throwing in like Eye of Newt and, Wolf's Bane and all this kind of crazy stuff. That was very much what the alchemists did. They had like a big pot. They threw stuff in there. They thought certain substances had different properties. Well, they do. And they were trying to put them in and trying to combine them in a way, say the correct magic words and so on to get really a potion at the end that did what they thought they wanted to do. So we're trying to really, it's like very much like Harry Potter. Like that was very true to what we understand the alchemists were trying to do. There's actually one very interesting story of one alchemist by the name, I remember his name, Hennig Brand was his name. And he actually thought of a good idea. He recognized that almost all metals are kind of like a silvery color, and that gold was different from most metals. Gold was yellow in color. And there's very few metals actually that aren't silver in color. There's a couple. Copper is another one. Gold, though, is yellow. And it's the only metal that they knew of that was yellow. And so he thought that whatever is making gold immortal might also be making the gold yellow. And then he made the connection in his brain that, well, when you go to the bathroom and you pee, the pee that comes out is also yellow, kind of golden color. And then he got thinking and he thought, well, maybe the substance that's inside of us that makes us alive is golden color. And every time we pee, we lose a little bit of it. And eventually, when we get old, we pee out all of our yellow substance and we lose whatever it is that's keeping us alive and we die of old age. So he was thinking, well, whatever's in that pee is really valuable. That yellow stuff, let's see if we can get it. And so what he ended up doing was he collected like hundreds of liters of urine. And I don't know how I don't think it was all his own, but he managed to collect hundreds of liters and he decided to boil it down. He wanted to get rid of the water and see what was left. And so he boiled like days. You probably wouldn't want to be downwind to this place when he was doing these experiments, but he boiled off the water, boiled it down, 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 down. Eventually it became like a thick paste, which was, we understand today what's in there. Lots of urea, uric acid, phosphates, other maybe organic compounds, salt, like these kinds of substances were all in there. He kept heating it till it went dry, and he kept heating it beyond dryness. And the temperature rose in there. And what happened is he noticed this waxy material started to form inside where the paste was. And he thought, that's unusual, because it was just sort of like a gross looking powder or whatever up to that time. And he noticed that it had this waxy material, and he had this long tweezers. And he went in and he grabbed that waxy piece and he pulled it up. And as soon as he pulled it out of the flask, it burst into a bright, like basically like an explosion of light. Like it wasn't loud. It just went and turned and filled the whole room with it's like you put a flash on a camera, and then it was gone. There was nothing left. It disappeared. And he was so excited because he thought he isolated the essence of life. Like imagine if such a thing existed and you isolated it, you'd go down in history forever as like discovering the essence of life. And it, for him, proved his hypothesis that the essence of life is constantly leaking out when we pee, and if we could somehow get that back into us, we might live forever. That turns out not to be the case. Don't drink your own pee. What it was that he got out of that waxy material was actually a substance called white phosphorus. And we know what the chemical reaction is. If you take phosphates and you heat it to high temperatures with organic carbon-based materials like urea, they'll react to make pure elemental phosphorus. And that's what he found. Phosphorus, as long as it was in the flask and being heated, it was stable. But if you pull it out into the air, it actually burns very, very quickly and turns into phosphorus oxide, which he, I guess, didn't see, but it shines very, very brightly. So that was actually a pretty interesting thing. White phosphorus is still actually used. I think it was used in war for a long time. I think during World War II, the Germans used to drop it over the city of London because they drop chunks of it all over the city. And what happens as soon as it lands, it'll catch on fire. So it lands on the roof of your house or whatever, it'll start burning. And what do you do when you see a fire? You pour water on it. And so water will put out the fire, it'll smother it, but eventually the water dries off. It doesn't do anything to the phosphorus. Once the phosphorus dries off and then gets re-exposed to the air, it catches on fire again. So you can put it out temporarily with water, but the only way to get rid of it is to like find each chunk and remove it, right? And then you can dispose of it safely that way. So it's a way to kind of like burn down a whole area, making it extremely difficult to actually put that fire out. So yeah, that was one thing at least that the alchemists gave us. One actually important discovery, and this is another popular passion of the alchemists, was purifying substances. That the substances that we know of, generally speaking, are complex mixtures of many different chemicals. And they spent a lot of time trying to purify these things, turn them into something as pure as possible. So if they found, like, I don't know, a bunch of leaves, they might try to find chemical techniques to extract different things out of the leaves and so on. And they actually developed a number of processes that we still use today. One of them being distillation. So what distillation is, really, it's taking a mixture, like a liquid mixture, you heat it, so you evaporate the liquid, it comes off as a gas, and then you then condense that liquid somewhere else back into the liquid form. So any solids that were in the initial liquid don't evaporate with it, so they're left behind, so you can purify liquids that way. And this is used certainly if you have like mixed drinks, like hard liquor. If it's anything above about 15% alcohol, that was created by distillation, by distilling something through natural fermentation. Recrystallization is another one. It's basically a way of taking a solid, dissolving it, and then slowly cooling it down so that it grows crystals. Those crystals are very pure generally. It's another way of purifying solids. So alchemists did give us a number of different methods for purifying different substances, which we still use today. This is sort of like a homemade still. So if you're making moonshine, maybe you've seen one of these. Here's my public service announcement. I make these occasionally in this course. Don't drink moonshine, okay? And I don't have a personal story to tell you about moonshine, but I have a secondhand story to tell you about moonshine, which is a good friend of mine. He went to university undergrad at UPEI, and he lived in residence And his RA, when he was in second year, went to a party where someone had moonshine, and he drank a little too much moonshine, and he woke up the next morning and he couldn't see. Like, he was blind. And he was like, what's going on? Probably had a bad hangover too. Went to the hospital. They say, yeah, that moonshine had methanol in it. You're blind now. Welcome to blindness. And he said he met up with him like 5 years later or something like that. And he had zero vision in one eye and like 10% in the other eye. So he had like got a little bit back, but he was still like mostly blind, couldn't drive, like all this kind of stuff. So I bet you he wished he spent the $25 and bought a bottle of something at the liquor store as opposed to getting the cheap free stuff somewhere else. So if you're ever offered moonshine, think about my story. It's not worth it, okay? Even if 99 out of 100 batches are totally fine, that's just a risk you don't need to take. Why would you take it? There we go. End of my story. And next question. What is an example of an important and lasting discovery made by the alchemists? Discovery of radioactivity, discovery of the elixir of life, purification methods such as distillation and recrystallization, development of the periodic table, discovery of the philosopher's stone. By the way, I think Harry Potter, the first book is called Harry Potter and the Philosopher's Stone, but isn't it called something different in like other countries? There's two names for it. You know what I'm talking about? Someone Google it. Let me know. Yeah, the Sorcerer's Stone. One of them is the Sorcerer's Stone, and they changed it to the Philosopher's Stone. I don't know why. I don't know what it is, but you're right. Yeah. Sorcerer's Stone, yeah, I see some online people saying the same thing. So maybe the movie is different from the books. I don't know. Whatever it is. I don't know why they changed it. I can't imagine either of them really being offensive, but what do you know? All right, so the alchemists did their thing for a long time, spent a lot of time doing things that didn't really pan out to a whole lot, except maybe purifying substances, which was good. In 1661, this book was published by a British guy named Robert Boyle. And he wrote one of the very first books, which represented a turning point in thinking about chemistry as a field away from alchemy and towards modern chemistry. And it was called The Skeptical Chemist. And he talks about the concept of elements. Remember those elements, way back, the classic elements? The idea of elements, as expressed here, just means fundamental substances that can be combined to make every other substance that we know of. And he talks about them here. He describes it. Maybe it was clear then, but it's not that clear to me now. I mean by elements certain primitive and simple or perfectly unmingled bodies which, not being made up of any other bodies or of one another, are the ingredients of which all those called perfectly mixed bodies are immediately compounded and to which they are ultimately resolved. So that's a long-winded way of basically saying all materials are made up of fundamental substances, some given number of them. We don't know, or they didn't really have a good idea then what those might be. They could be mixed together to make every substance that we know about. We're going to jump ahead 100 years. There was another chemist, and this time we're moving to France, named Antoine Lavoisier. And he actually came up with a very important discovery. And it was the law of conservation of mass. So this is a scientific law. What does that mean? It's an observation, right? It's an observation, often can be expressed mathematically, but not always, but doesn't provide any explanation for why this might be the case. It's just a statement of fact or a statement of truth or a statement of repeated observation. And really all the law of conservation of mass says is what we talked about before, which is when you have a chemical transformation or a chemical reaction, whatever mass you had to begin with you have to also have that same mass at the end. You can't create mass, and you can't have mass disappear into nothingness. So we understand that today to also mean if you have atoms at the beginning, all those atoms still are present at the end. They don't change their mass at all when you do a chemical reaction. So there's a picture here. Basically, it's a reaction of baking soda and vinegar. You might have done this reaction in the kitchen at some point as a kid. You mix them together and it fizzes. What we're looking at here is a little container, a little flask, called an Erlenmeyer flask, which has vinegar sitting in the bottom. And then there's a balloon put over the top, and inside the balloon, kind of flopped to the side, is the baking soda. Notice the mass. You can see it's sitting on a balance. It says 38.61 grams, just like a regular kitchen balance. Grab the balloon and shake the powder inside. The chemical reaction starts happening, gives off CO2. It starts to inflate the balloon, and you can see the balloon inflates. At all points in time along this reaction, the mass doesn't change one bit. It's always 38.61. And that's true when you have any chemical reaction, the mass always remains. Now, this wasn't obvious to people at all at this point, because you take a candle and you light it on fire, what do you see? The candle's big, burns, candle's small. Obviously, something disappeared. But what Lavoisier said is what's going on there is the candle is reacting with oxygen in the air. It's also putting off some other gases, which we know are CO2 and water. And if you weighed all the CO2 and water that you got as products, and you weighed all the oxygen and wax you had at the beginning, those two numbers have to be exactly the same. You can't just have that disappear. It's got to remain. And this is known as the law of conservation of mass, 1870s. Okay, so I have a question for you. Not a question you have to answer online or anything like that. So let's say that you are trying to lose weight. And so you diet and exercise or whatever. And let's say you're successful in losing 10 pounds. What happens to those 10 pounds? What happened to the fat that was on your body before and now isn't on your body? Where did it go? Right? And there was a survey done a number of years ago where they asked this question to professionals whose job it was to sort of coach people and guide people into maintaining a healthy weight. And they asked 3 groups of people. They asked dietitians, they asked personal trainers, and they asked medical doctors. And they asked them, what happens to fat when you lose weight? Where does it go? And these were the options they could pick. It's lost as energy or heat. It becomes muscle. It's excreted in sweat and urine. It's excreted in feces. It's converted to carbon dioxide and exhaled. Something else, or no idea. And so they asked, I don't know how many of each of these groups of professionals, what their answers are. And I just want you to think for a second before I jump to the results, what you think is the answer. What do you think happens? The correct answer is one of these, and only one of these. Well, this is what people said. And you see we have family doctors, dietitians, and personal trainers. The majority of all 3 groups picked it's lost as energy and heat. So you burn it off, right? Turns into heat and energy. You can see some say feces, some say muscle, some say sweat, urine. Some just didn't know. The correct answer is turns into carbon dioxide and it's exhaled. None of the doctors said that. None of the personal trainers said that. And a small percentage of the dietitians did say that. Dietitians, by the way, do a lot of chemistry. So I'm happy to see some of them getting this one correct. But we just stated the law of conservation of mass. It says that in a chemical reaction, you can't lose mass. Mass goes somewhere. Just like when you burn a candle, the candle just doesn't disappear. That turns into carbon dioxide. That mass remains. It goes somewhere else. In that case, is a gas. You can't just have fat turn into energy or turn into heat. The fat molecules still have to exist. All those atoms that were in your body before are somewhere. And in that sense, maybe excreting them through sweat or urine or whatever else is maybe not a bad choice, not as bad of a choice as some of the other ones, because at least then those atoms are going somewhere. But the correct answer is CO2. That in your body and your cells, you're burning fat molecules. It gets converted to CO2. Every time you breathe in oxygen. Every time you breathe out CO2. So you can almost think of that process as like oxygen goes in, grabs a carbon atom, and goes back out. Takes that carbon atom with it. And that's how you lose mass. That's where fat molecules go. Turns into water as well, but water has its own sort of system in our bodies. So very interesting that what is an extremely fundamental idea and very old idea in chemistry and super fundamental to our understanding of how reactions happen, how change can happen in matter, is still not really well understood by people whose profession it is to help people with these sorts of processes. The family doctors one is a little bit disappointing because they actually do quite a bit of chemistry too, and they write MCATs where there's chemistry involved. And I mean, I don't know exactly the context of how this was asked, but I was hoping for more of the correct answers there. But when I asked this question in the class, I've asked this to my class before in previous years, most people pick energy heat. Most people, it's like the same breakdown. Not a lot of people pick the CO2 and water. So Lavoisier, he formalized that as a law, which doesn't mean it's absolute and true. In fact, there's exceptions to it. When you have nuclear reactions and you split atoms, we know that the mass actually changes a little bit. It's called a mass defect. So there are exceptions to the law of conservation of mass. But again, by and large, chemical reactions that we're doing, either biochemically in our bodies, burning something, you name it, that law is true. All right. So Lavoisier expanded on the idea of Robert Boyle of elements, and he identified what he thought were the known elements at the time. So he took all the elements that were understood to be the simplest possible substance that weren't made of other things, and he listed them all, and he wrote a book. And the book was called Elements of Chemistry. He's French, so it was, I don't know, I'm not going to attempt to say that in French. And what I have here is a picture of our modern periodic table with only some elements in it. So these elements that are here were the ones that were known at the time, 1789. As you can see, like there's many of them that are missing, but they did know about these ones. Carbon, of course, they knew about gold, they knew about, iron, and some of these other ones that are on there as well have been known for a long time. So he wrote this particular book. He died in 1789, soon after this was published. 1789 was a busy time in France. Not sure if you're history buffs, but French Revolution was taking place at that time, and he was beheaded with a guillotine at the time. And what his crime was is he was working in a university, and often when there are revolutions, we'll say, the educated class is maybe often or sometimes, or at least sometimes, looked upon with suspicion. And this was definitely true during the French Revolution. The other thing is he stood up for one of his colleagues who was not from France. So he had a non-French born colleague that he was trying to protect, and that was seen as a crime at the time. So he was arrested, tried in what they called were kangaroo courts, which were courts that were just, a formality, and then they executed him with guillotine, and they gathered his things up at the university and send them to his wife, which was pretty distressing. I think it was like a few months later, the French authorities issued an apology for cutting his head off. And I forget who said this, but there was a famous person that said it only took them a minute to cut his head off, but it would take them 100 years to develop another head as brilliant. I probably massacred that, but anyway. you get the idea. I'm going to get just a quick 1 minute to answer some questions that have showed up in the chat. The first one is question about the assignment. Does it need to be an article about a chemical on the periodic table or chemical compound? Yeah, chemical compound doesn't have to be an element. It can be anything. So that hopefully answers your question, Emily. Yeah, okay, good. A little bit of chatter there. So yeah, Lavoisier came along. He wrote the first, what's considered first chemistry textbook called Elements, listed the elements out at the time, and pretty much wrote in this book everything which was understood about chemistry in the 1780s, which by today's standards wasn't really a whole lot. Around that time, a budding young chemist named Humphrey Davy, who was across the channel in London, became very interested in chemistry and picked up a copy of Lavoisier's book on elements, read it several times, mastered it, and really at that point in time, you could argue he knew everything there was to know about chemistry. Like that's almost impossible to do today. A whole lifetime, you could never know 1% of what is known about chemistry. But at the time, wasn't too bad. By age 18, he had done that. And he started doing his own investigations, which again is not something that is really recommended anymore. Home labs are often looked at with suspicion because usually the purpose of home labs is illicit. And it's often dangerous. And anyway, at the time though, safety wasn't really considered the same way. He wrote papers when he was 20 clarifying the nature of energy. When he was age 21, he discovered a method to produce a new substance, a new gas that people didn't know about at the time, called N2O, which he didn't know it was N2O at the time, but he knew it was a nitrogen and oxygen combination, which we now know this is called laughing gas. And he experimented with it by just breathing it in himself. And I can't imagine, I can't stress enough how dangerous this is. You just make some random mix of gas and let's see what happens when I breathe it in. Because it could have been hydrogen cyanide gas and it would have just killed him. But it wasn't. And it got him high. It got him giddy and laughing. And he thought this was pretty cool. He would have parties where he'd have people over and he built this like chamber where you'd be breathing in laughing gas. And he wrote all these, like, he was very kind of a flowery guy and he was very like larger than life, and he wrote poetry about hallucinations he would get when he was high on this stuff. And anyway, he was pretty interesting. He actually suggested that this would be a good thing to give people before surgery, and about 100 years later they started doing that. Took them a while to take his advice, but if you go to the dentist today, you can get laughing gas, or if you're in the hospital and you as a sort of a low level pain management. So it's sort of one of the first things if you are giving birth, for example. It's one of the kind of the first, before they go to like I forget the word for this, when they give you the needle in the back, epidural. Yeah, that's sort of like, then you don't feel anything anymore. This was sort of a lighter phased in approach. You can get laughing gas. Anyway, he kept going. He became interested in batteries. And there was another physicist by the name of Volta who was building batteries. And he started copying the design and was building his own batteries. And he theorized that there must be some chemical reaction happening in the battery that's producing electricity. That there's some relationship between chemical change and electrical energy, electricity. And this picture here shows, on the table, you can see all those like rows. It looks like rows of things. These are all like individual cells of a battery piled all together. And he'd take like one metal, I think like copper, and put a piece of like wet paper. And then he would put another metal, which would be tin, wet paper. And he kept sandwiching these. And it took up this entire table. He made this really big battery. Probably not very efficient, but by making it large enough, he made it functional. And on one end, he had like a wire, and the other end, he had a wire. And if you touched them, he would see sparks. So he knew there was electricity flowing, and all he had to do was complete the connection. So then what he started doing was taking this big battery he built and sticking the 2 electrodes into various substances to see what would happen. And one of the first things he did is he took a dead frog and he started zapping the frog with these electrodes to see what would happen. And what he noticed is the dead frog's legs would kick when he touched it with the 2 electrodes. And he thought something about the way our muscles move must be related to electricity, because electricity can make a dead animal contract its limbs. And he talked about how, somehow they're trying to figure out how life works too at this time. That had very kind of poor understanding, but he realized there's sort of an electrical component there. He, in his mid-20s, he decided just to stick them in a thing of water to see what would happen. And what he noticed is when he stuck the electrodes in water, bubbles started to form at the 2 electrodes, which he collected, and he discovered he made pure oxygen on one side and pure hydrogen on the other side. And he was the first person to discover that water had 2 parts hydrogen for 1 part oxygen. So just by this sort of random experiment, he discovered what water is made from, what elements it's made from, and the ratio of those elements to make water as well. And he realized you could burn them, put them back together, and remake the water. He kept doing the same thing with different substances. By the way, you can do the same experiment yourself with a battery. You can split water into hydrogen and oxygen. Hydrogen here is the right side because you can see it's got twice as much gas as the left-hand side. He started taking salts like potassium chloride, sodium bromide, things like this, and he'd heat them up until they were a liquid and stick his electrodes in that as well. And what would happen is he noticed gas would form on one side, a green gas when he used potassium chloride, and a metal would form on the other side, and if the metal was put in water, it would explode. And what he then discovered through doing that is he'd be able to split potassium chloride into potassium metal and chlorine gas. And he realized he was taking all these different salts and he was decomposing them into the basic elements that they were made of, and he was able to discover a whole bunch of new elements. He discovered calcium, magnesium, strontium, barium, boron, potassium, sodium, chlorine, later on iodine. So many elements. He just kind of did the same one trick and was able to discover, like basically almost doubled the size of the periodic table, the known elements at the time. He had theories about how this would work. And what he did as a backdrop to all of this, he loved the limelight. He loved popularity, the spotlight, all this kind of stuff. And what he used to do is go to big lecture halls in London, and he would do chemical demonstrations. He would show everybody who would come different experiments he was doing. He would make chlorine and he would throw the potassium into the water, watch it explode, all these kinds of things. And it was like a full house. It was packed every time he would go do one of these things. Because, I mean, you could say, well, they didn't have video games and TV and movies and stuff like that then. So, entertainment was maybe hard to come by, but they certainly had theater and music and all that kind of stuff. So it was no exaggeration to say that there was a very real public fascination with the advances that were happening at that time in chemistry and science in general. Big year happened in 1812 for him. He turned 34. He was knighted, which is kind of a big deal. He was the first scientist actually knighted since Sir Isaac Newton. He also got married that year, and he went on his honeymoon. His honeymoon was to France, to Paris, which wasn't too far. And this is what he brought with him: an air pump, an electrical machine, his battery, that one the size of a table, that giant thing, blowpipe apparatus. This is for like making fire, bellows in a forge. So this is so he could make his own glassware, like make flasks and stuff like that by melting glass. Mercurial and water gas apparatuses for measuring gas pressures, cups and basins of platinum and glass, and all the common reagents of chemistry. So he kind of took like a mobile lab with him. And his honeymoon wasn't like a romantic getaway. It was like a chance to go do science and meet with other minds at the time. So his first stop, he also took his research assistant. So I don't know, like if you're going on your honeymoon, that's definitely something you should leave behind, is your research assistant. Michael Faraday, who in his own right became a very famous chemist later on, arguably more famous, actually. Um, so anyway, his first stop was to Paris. He met with two scientists there, Ampere and Gay-Lussac, and they had discovered this black substance that they had isolated from seaweed. And so he did some experiments with them and worked with them, knowing what he knew, and they were able to identify this as a new element, which is called iodine. He predicted there must be another substance like iodine called bromine, which, of course, is a real thing, which was discovered later on. So he had a pretty good understanding of the chemical elements and so on. So again, this is our periodic table. All the black ones were all the ones that Lavoisier had put in his book, Elements of Chemistry, back in 1789. All the blue ones are ones that were added in by Davy. So maybe he increased it by what, like 50%? So he added quite a few new elements, and it's starting to kind of fill in this. And of course, they had no idea about this arrangement of elements, this periodic table that I'm putting these in. This is me putting them into a modern table. But people were starting to think about the relationship between the known elements and why, like what made one element different from another element, which at the time they had no idea. Like what made oxygen different from iron, they had no clue. They just knew they were both fundamental substances that could not be broken down. Mary Shelley was an attendee at one of his big demo shows. And he had done the demo there where he took the electrodes and zapped the frog legs and made the frog legs kick. And she was there and she said this, a new influence has been discovered which has enabled man to produce from combinations of dead matter effects which were formerly occasioned only by animal organs. Does anyone know who Mary Shelley is? Yeah, she's a famous author, and I don't have the slide anymore. Her famous work is Frankenstein. And think about what happens in Frankenstein. Dr. Frankenstein in the book collects dead body parts, sews them together, takes a big battery, goes bzzz, and it comes to life. Think about where that idea probably came from, right? Probably attending one of these lectures and seeing the same thing done with the frog legs. All right. 2 questions. First one. If we go on a diet and lose 10 pounds of fat, what happens to the carbon atoms that are lost? Lost in quotations. The carbon atoms are destroyed and cease to exist. They are excreted in feces. They're converted to CO2 and exhaled, or they get converted into energy. We have another question as well. It says, which chemist postulated the law of conservation of mass, wrote the first chemistry textbook called Elements, but was killed by guillotine in the French Revolution? Marie Curie, Albert Einstein, Antoine Lavoisier, or Humphrey Davy? Davy also was famous. He invented a lamp that it was based on like a flame that you could bring it down into a coal mine and it wouldn't cause it wouldn't cause explosions with methane gas. It's called the Davy lamp. And I think it was used for hundreds of years, and it was like a revolutionary thing because it allowed people to bring light into mines safely. Just another small piece of his legacy. It's 3:41. I think we're good. Okay, I don't really want to jump into the next couple of folks. But we're going to continue our journey through the history of chemistry. We're like halfway through. We're speeding along. We're skipping a lot of people. It's not like we're going to hit every single person that had an important idea in chemistry. But some ideas that we probably will be coming back to, I do want to hit. And we'll leave things right there. Any questions from anybody? I guess the online folks are like 10 seconds, 15 seconds delayed. But yeah, if you have any questions, pop them in the chat, let me know, and that's it. So it's nice to see more people arriving in person, and even more are welcome to come next time. I'm looking at you people online. Yeah, we can hold, I think, 100 people, so we can take another 88 next class. And I think the COVID scare is pretty much over. I shouldn't say globally, it's certainly not, but the Acadia case, yes, I'd say so. All right, thanks everybody, and we will see you early next week.